Hi everyone, welcome back. Today we're on section 21, indexed unions and intersections. So first thing I want to do is I want to recall some facts we knew before. So if these things are sets, then we know that A1 union with A2 union A3, well, that's kind of associative, right? So we get to move those parentheses. Okay, and now similarly with the intersection. Okay, so I just want you to remember that it doesn't matter if we're talking about just unions and intersections, it doesn't matter what order we do them in. Okay, so like if this was a union and if this one was a union and this one was an intersection or something, then stuff gets weird, it gets different. But if we're only talking about just unions or just intersections, it doesn't matter necessarily what order we do them in. Okay? So a question that we may have, or someone else maybe, is what if we want to take the union or the intersection of many, many sets or an infinite number of sets? I realized that my wording was a little bit confusing. I had originally said infinite sets, but what I mean is like an infinite number of sets, okay? So our answer to this question is going to be, excuse me, is going to be new notation. Okay, so here's what we're going to do. So if we want to take the infinite union of something, so like let's say we want to take the union of an from n equals 0 to infinity. So as you notice, it's like a big union sign, right? It's just much taller. It's as tall as a capital letter, okay? And we're indexing it just like we would if we were trying to talk about the sum of I plus 1, maybe, from I equals 0 to infinity, right? So then it works the same way. So we start at n0. So what this is this is A0 union with, and then we go up 1, A1, we go up 1, A2, and we just go on and on forever into infinity and beyond, right? So similarly, if we want to talk about intersections, it's like a capital intersection, right? It's just a bigger intersection, okay? So A0 intersected with A1, intersected with A2, intersected with blah, 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 blah. Okay? So a natural question you might want to ask is, well, does it always have to go to infinity to use this notation? No, you don't. So just like up here with our sigma, sometimes we go from I equals 0 to like the letter L or something, or maybe 4. If it's 4, sometimes we just write it out. But let's say it's like 26 or something. So we don't want to write every single version out. So maybe it's like I squared or something. I don't know. Okay, so it's a similar thing. So you could just write n equals 0 to 24, or maybe m. Maybe m's an important, maybe you're doing an induction proof and you're doing induction on m, the letter m. Okay, so the only difference that I would write over here, is now we have like an ending spot. Okay. All right, so this is just the notation that I'm trying to go over now. This is how you would write it in general. Okay, so let's try some examples. If you're feeling confident about this and you want to give it a try, or maybe you're not feeling confident, but you just want to give it a try, see what happens, because oftentimes when we fail and we learn from our failures, that can be when a lot of learning happens. Okay, so you could try these on your own. You could pause this, but I am going to give a small hint as far as a strategy that I like to use that I think really helps students see things easier. But first, what may have drawn your attention, or maybe you paused the video, you tried it, and now you're like, what the heck? So you're coming back to the video. This one down here. So this n is in the integers. Okay. let me first start explaining what that means by saying that this one up here is the same as n in the natural numbers. So what that means is we're allowed to let n range over any natural number that we want. And in fact, it ranges over every single natural number, okay? So those two things are the same, right? If you can say n equals 1 to infinity, well, that's the same as n being in the natural numbers. Because remember, our natural numbers don't include 0, ours, for this class. If you get a different class, it might be a little different, but okay. But for the integers, we can't like say let n equal negative infinity up to infinity. That doesn't make any sense. You can't actually equal negative infinity or infinity. You can't equal that, right? So, well, so what I mean by that, sorry, let me backtrack a little bit. Because you might say, well, Danica, you can say that a size of a set is equal to infinity, so why is this any different? Well, this is different because once we pick what n is, now it's fixed. Now it's a finite number, okay? So you can't let n equal infinity. You can let it range up to infinity or down to negative infinity. So if we let n range over the integers, maybe what you do is you think, because remember, it doesn't matter what order you union these things in. So maybe what you do is you start with A0, then you union A1, then you union A negative 1. Okay, and dot dot dot. And maybe on your maybe you just have this equation that by this point you're doing this, and it just goes on and on forever. Okay, so I hope that makes some sense, how that would all work out. Okay, so now for the strategy. Now that we've gotten some of the notation out of the way, my strategy that I like to show students is try the first couple. Okay, try unioning the first two iterations. So for this one, maybe you do maybe you think of every number in its negative as one iteration. So like this is an first iteration, second iteration, or something, however you want to think about it. Okay. Actually, that's an interesting idea. So we could rewrite this as the union of n equals 0 to infinity. If we want to be really particular about it, well, it's the same, of a n union a negative n. Right? So 0 equals negative 0, right? But if we union the same two sets together, you just get that same set again. Okay, so it doesn't change anything for us. Okay, it's interesting. Anyway, so try doing the first two iterations union together. Okay, and then try the next one tacked on to the end of that. Okay, and then maybe even, so we're on the real line, right? So, because remember, this thing means, like on this real line, here's I and here's I plus 1. We go from here to here, including those 2 points, okay? So you can even try drawing it on the number line. But here's the kicker, is you're looking for a pattern. You're trying to see where it's going, okay? So I'll write that somewhere, maybe below. So maybe you won't see a pattern right away, or maybe you kind of sense there's a pattern, but you're not exactly sure. You could just keep doing it over and over again. But if that's not helpful to you, that's fine as well, You can try lots of other things, but this is what I've found to be most helpful with the students that I've taught in the past. So this is what I'm going to show you. Okay, so I'm going to do the problems now. All right. So this first one here, so let's think about A1 union A2. So who are those? So A1 is 1 to 2, union 2 to 3. Okay. All right, so what is that? That's just 1 to 3. Okay. And so if I did A1 union A2 union A3, what does that look like? So that's 1 to 3 union with 3 to 4. Oh, okay. All right. So I kind of see where this is going now. So we just keep adding one integer on to the end of our thing. So this is equal to okay, this is equal to, oh, not 0, sorry, 1 to infinity. So remember, infinity is always an open bracket, so it's negative infinity. All right, okay. So how about this next one? And so this one, I'm not going to go through actually proving it. We'll see some examples of that, but you should probably already know how to do that, okay? You want to show inclusion both ways, but I'll show you some examples of it. So this next one is going to be kind of the same deal, but this time we're starting at 0 and we end at n. Okay, so our interval is going to look like this, and then what's the last one? This is what trips people up sometimes. Well, it's going to be n plus 1. Okay. All right, so this crazy mess that we have over here, well, this one's going to be negative infinity to infinity. For similar reasons to above, but just on both sides, right? And including 0. All right. Okay, so now on to our next example. Bm is the set including m and m plus 1. So a big difference between this one and the last example that we went over is this one only has 2 elements in it, okay? Remember, that's what these brackets are all about. It's a set including those 2 elements, okay? All right, so what does this look like? Well, another strategy you could use is, you know how before I was writing out like this and I went on and on. So maybe somewhere in the middle it's like L and L plus 1 or something. I don't know. It goes on and on forever. Okay, so that might be another strategy. Maybe that helps some people. It's just writing out what we're unioning. Okay, so what do we get? Well, we get all the integers minus the negative integers. Okay, so who is that? That's like the naturals union 0. Okay, so now let's talk about definitions and terms that you would use on a proof. Okay, so in general, for AI sets and integers, let's say, I don't know. Okay, in general, for AI sets, I in some set I, so I is what we call an index set. So why we call it an index set is because it's going to define the index of A, okay? So it's just a set of numbers. So maybe it's the integers, maybe it's the natural numbers, maybe it's 0, 1, 2, 3, 4, all the way up to like capital N, whoever that is. But this is just a generalization. So the union over the index set I of AIs is equal to the elements such that X is in AI for just some I, okay? So it doesn't need to be in 2 or 3, it only needs to be in 1. Okay, maybe it's in all of them, but it doesn't matter because it just needs to be in 1. So how about the intersection? Well, this is going to be all the elements X such that X is in AI for all I in our index set, okay? So it has to be in every single one of our sets. Okay. All right. Okay, so let's go back to our example before where Bm is the set M and M plus 1. So I'd like you to try these on your own. Now notice who we're indexing over. Now we're indexing over the reals, so stuff is getting kind of crazy. Okay, you could pause this and come back, but I'm going to talk about a strategy.
So the use of our strategy, we don't have normal iterations. So let's just pick two elements in R. Okay, let's say X in R, and then let's say X plus 2 in R. Because both of those are definitely in the reals, right? If X is in the reals, X plus 2 is in the reals. Okay, so what would B sub X union B sub X plus 2 be? Well, it would be X plus 1, X plus 2, oops, getting ahead of myself, and X plus 3. Okay. All right, so then how about the intersection? Well, as you probably already guessed, it's going to be the empty set. So if we find that any two random ones, their intersection is the empty set, then there's no way that if we intersect more stuff, if you intersect anything with the empty set, you just get the empty set back. Okay, so boom, we already figured that out. Now, how about the union? You pick any real number, and you can just do B of that real number. And that's going to be in the union, so that gets tossed into our salad bowl, or however you want to picture it. So this ends up being the reals. Okay, well, I promised you an example of a proof, so let's prove it. All right, so not the empty set. That would be a fast proof. But proof of the union, yeah, let's write it out. Okay, so we're just going to approach this similarly to how we show that any two sets are equal. Okay, so we start with this direction. So let X be some element in here. Okay, so what does that mean? Well, that means there exists some, let's say, M in the reals, such that X is in BM, right? Because that's the meaning of our index union, okay? But what is BM? BM is M and M plus 1. Okay. So X equals M, or X equals M plus 1. Since M is in the reals, then X is in the reals in either case, right? Because if M is in the reals and M plus 1 is in the reals, so it doesn't matter who X equals, we'll still end up in the reals. So that gives us that the union BI is a subset of the reals. Woohoo! Okay, let's try the other direction. Let X be a real number. Okay, well this one's a little bit faster. But so you might already see where we're going, but maybe what you would want to do is talk about what you want. So what do I want? I want some BM such that X is in BM for M in the reals. Okay, so that's how you would kind of think about it in general. Maybe you talk about who BM is. So BM is like M plus 1. So you could think about that. But as you probably guessed, we're going to pick BX. Or you could pick BX minus 1 if you wanted to be fancy. So consider BX. Okay, but we're not done yet. So BX equals X comma X plus 1. So let's add in that since we're allowed to do this since X is in the reals. Okay. All right. So X is in BX. And since BX is a subset of the union of all these BIs, then X is in our union. All right, cool. So it's not just as easy as just stating this. You have to give us some explanation of why you're allowed to do B sub X and why it's in the union, yada, yada, yada. Okay, then the reals is a subset of the union. Therefore, excellent. See you next time.